Hello and welcome to another session in physics. In this session, we will be looking at the topic work, energy and power. But before that, let us review the previous lesson. Welcome back. At this point, I'd like us to take the definition of work. We say that energy is the ability or capacity to do work. So work basically is a function of. But then at this point, there is another definition for work. It is not just when we use up energy that we're said to be doing work, but we can also be said to be doing work whenever a force moves a body through a certain distance in the direction of the force. So we can see that work can be defined as the product and displacement. So basically what we're saying is that work is equal to force times displacement. Also remember that it is a scalar quantity and it is measured in joules. The SI unit is in joules. As you can see from the diagram here, you notice that a man is applying a force to an object and is trying to push that object. The magnitude of the force that this man is applying multiplied by the displacement, in other words, the distance that has been moved, object is what we call work done. Notice too in this particular image that this woman has done work by lifting a sack of bag from the ground to her head. But because this woman is standing at a spot, she isn't really doing any specific kind of work. She is standing at a spot, she is not doing any work. But she can only be said to be doing work only when she starts to move. Alternatively, underneath is doing work because he is applying force in a direction and this man is said to be moving. So for that reason, we say that work is equal to force times distance or displacement. Also, we can say that work is equal to mgh, which is the mass of the body, times g, due to gravity, and h, which is the height of the body. But what if force is applied on a body at an angle theta to be horizontal? It's important to note that when it comes to angles and it comes to force, we have the horizontal component of the force, and then we have the vertical component of the force. At both times, when we want to calculate the work that has been done by a body moving at an angle, we use F cos theta times d, where cos theta is the angle of inclination, as you can see from the diagram there below. Now let's talk about energy. Energy is the ability to do work, like we said earlier. It is a scalar quantity, and of course, it is measured in joules. We have so many forms of energy, which include things like mechanical energy, thermal energy, chemical energy, electrical energy. We have nuclear or atomic energy, and then of course solar or light energy, and then we have sound energy. Thermal energy has to do with heat, chemical energy has to do with chemical reactions, electrical energy has to do with the movement of electrons, electricity, and then nuclear atomic energy has to do with processes such as fission and fusion. It's the breaking down of heavy nuclei into smaller components, or the coming together of atoms so that a huge amount of energy is released. Then, as we all know, solar has to do with the sun. It is energy that comes from the sun that helps us to dry our clothes, helps to keep our surroundings warm as well. And then sound energy is the kind of energy we get from music instruments such as percussion instruments. We also have stringed instruments and so on and so forth. So the vibration of these helps to produce sound energy. At this point, let's talk about the first one, mechanical energy. We have two types of mechanical energy. They are potential energy and kinetic energy. If you look critically at the image here down, you would notice that the two bodies that are moving, the boy moving upwards on the bicycle and heat coming down at the same time. At these 2 points, they possess kinetic energy. But at this point here, the boy is stationary. He is at rest. He is not moving at this instant. He's just resting on top here. At this height here, this boy possesses what we call potential energy. And that brings us to the definition of potential. So what exactly do we mean when we talk about potential energy? Well, potential energy is energy possessed by a body at rest. A body at rest. A body that has stored energy. A body that has stored energy. So, when we talk about potential energy, an example is an orange hanging on a tree, a book resting on a desk, a cup that is resting in the kitchen. These are examples of potential energy. When you sit on your chair, you're not moving, you possess potential energy as well. But then it's given by the equation dE equals to mgh, where m is the mass of the body, and this one is acceleration due to gravity, which has a value of 10 meters per second squared, and h is the height of that body. When we talk about kinetic energy, kinetic is the reverse or the opposite of potential energy. And this is energy possessed by a body in motion. Potential energy is by a body at rest. Kinetic energy is possessed by a body in motion. So, for a body to possess kinetic energy, that body has to be moving. And that brings us to the formula for kinetic, which is equal to half mv squared. M is the mass of the body, and v is the velocity of that body. M is the mass of the body, and v is the velocity of that body. So, at this point, I'd like us to take just one example to help us state what we're talking about here when it comes to kinetic energy. So, we're asked to find the kinetic energy. Find the kinetic energy of an object. An object of mass 5 kg moving at a speed or velocity of 15 meters per second. 15 meters per second. So, very simple. Remember that kinetic energy is given by half mv squared. So kinetic energy is going to become half times the mass of the body. Mass of the body is 5 kg. The velocity of that body is 15 per second. So half times mass of the body, 5 times 15. Remember, the velocity is squared, so it's going to be 15 times 15. So here, when you multiply everything together, we're going to have 562.5 joules. That is the kinetic energy possessed by the body. At this point, let us talk about power. Power is defined as the time rate of doing work, or the time transfer. It is a scalar quantity, and its unit is watts. When your parents ask you to go and buy a bulb, you get to the electric shop and you tell them you want a bulb of like say 100 watts, or you want a bulb of like 200 watts, or energy bulbs like 40 or 60 watts. Watts is the SI unit for measuring power, given by work done and the time that is taken to do that work. And you and I know that work done is equal to force times distance and divided by the time itself. Also, power is given by force times you know that distance divided by time, or displacement divided by time, is velocity. So force times velocity, power as well. Alright, so let's take this question that says a boy of mass climbs up 10 steps each of height 0.2 meters in 20 seconds, and we are asked to calculate the power of the boy. So first of all, let us see the height that was climbed by this boy. The height that was climbed by the boy. Remember, it was, and each of these steps had a height of 0.2. So it's going to become 10 times 0.2 is 2 over 10. 10 will cancel 10, equal to 2 meters. That was the height of the staircase. Now the mass of the boy is 10 kg, and the time that was taken for this whole climbing was 20 seconds. The power of the boy is going to become work done over time taken to do that work. And the work done is mgh over t, which gives us the power. Now we come over to the next one. The mass of the boy is 10. 10 times 10, which is acceleration due to gravity, times 2 meters, which is the height, divided by our time, which is 20 seconds. Our time is 20 seconds. So we're going to have 0 will cancel 0, 2 will cancel 2. So 1 is 10 watts. 10 watts is the power that was used up by the boy. At this point, I'd like you to refresh your memory on what we just discussed, and thank you for joining me in this lesson. And please take the test that will appear on your screen. So